20 videos on data science. Today we are beginning with a new topic, what is called proportional integral derivative, that is PID. We would like to give an introduction about this in this video, and before we try to explore how this can be done using machine learning. So the basic principle looks like that. Suppose you simply take a heater, apply a constant voltage across the heater and try to measure the temperature. You will see that the temperature will rise like this. Suppose I would like to stop the temperature at 50 degrees centigrade, like the line drawn here that we call the set point, then it won't stop at 50 degrees. There are many reasons why it won't stop: the surroundings and also the power applied, so many such things. So you will never be able to stop at 50 degrees. Now the PID is a technique to stop exactly at 50. Now how do you achieve that? You achieve this through this block diagram. What you do is you read back the sensor temperature and also you give a set point of 50 degree. You take the difference between that, but that is what we call error with respect to time, ET, and that is fed into a temperature controller which will produce a power which is going on varying with respect to time automatically according to PID algorithm, and the power goes into the heater temperature. Again, the so-called process variable, that is the sensor temperature, is measured back. So this is a closed loop system. Now the PID equation is a mathematical model that describes how system responds to a disturbance. See the earlier diagram, the set point, now I call it RT, process variable I bring it here, and you know what you do is actually you implement a PID algorithm which looks like that. PID algorithm says you take a multiplication of error over time and also integration, addition of all the errors and also difference of errors, and then add them together, and you know the final output what you get is being fed to power the heater, and from the heater you can again the temperature can be fed back to have a closed loop mechanism. So I can always say that mathematically ut is equal to kp is a proportional constant multiplied by error plus integral constant and integration of all the errors, addition of all the errors, plus kd, the differential constant and difference of errors. And now these are called kp, ka and kd. It incorporates proportional, integral and derivative terms to adjust the control output and maintain the system at the desired set point. So as you can see on the screen, what is the effect of kp, ka and kd when you have a set point which is in this dotted line, and you know how this algorithm, the powerful algorithm, is able to implement it, the PID algorithm. You will be able to see the effect of all these three constants. Now how a simple Python program can work as a simple PID control function, nothing but a PID algorithm. So that is what we will call it now, a PID simulation program. The program will simulate the operation of a PID controller in a temperature control scenario. So the program is used on the principles of PID control, a widely used control strategy in engineering. So how you can do through a simple programming technique, but later we are going to take this into a higher and higher level of machine learning, which is a very new topic. So in a simple Python program, how do you implement this? So we have three constants, that is what I said, kc, tau I and tau d. Right now I will give some random values, 6, 75. This is tau I is integration time, so it will be in second. The tau d I will keep it 0. So we are going to have more a PI controller instead of a PID controller. D is almost this D is kept as 0. Now, in programmatically, if you try to write an algorithm, it will look like that. You can write in any language. In Python, it would look like that. You will create a function or module called PID, which will have certain parameters: set point, process variable, and PV, process variable last, that means the previous value, and I error, right? This is what is the integral error, and dt is the time step. In every second you are taking data, every millisecond you are taking data, that is a dt. Now the capital Kp is equal to Kc. Capital Ka is the real parameter which we are looking for, proportional constant. Integral constant is Kc divided by tau I. Tau I is a number which we divide, that is the constant which we are given as 75. And then Kd, capital Kd is Kc multiplied by tau d. Now Kc is the proportional gain, tau I is the integral time constant here, and tau d is the derivative time constant. The set point is equal to the desired value that system should achieve. PV is the process variable, the current value of the system being controlled, and PV underscore last is the last process variable value, and I error is the integral of the error, dt the time step. So you can see these constants have been already explained in this particular screen. Now the function is continued. As you know, the function started from here and I'm continuing in this page. So the first few things like OP is equal to 0. That means this is called, there is something called a bias. Output voltage is an addition of a bias. Initially when some heater is put on, suppose you don't want the heater to be off, you want to give certain bias, some DC voltage. That is what is called OP0. So now I can also, right now I am giving it as 0. I can give 0.1, 0.2, 0.3 or 30% of the power, whatever. But right now I am giving it 0. These are upper level. You are trying to vary the power between 0 to 100%. Now the error, the first variable is SP minus PV. We know that the difference between, so as I had shown here in the first diagram, see that the difference between RT and this what is coming in, or this between these 2 points, that is what it was. So remember that. Now error is equal to SP minus PV, and calculate the integral error. I error is equal to I error plus Ka into error multiplied by dt. That is the integral error, and calculate the measurement derivative, that is dt. If dt, minimum dt we have put like 100 microsecond, so it's like not exactly 100 microsecond, 10 nanosecond, that is 1 e minus 8. 1 e minus 9 means 1 nanosecond. So it won't be any less than that. So this line is says actually if it is greater than that, make it work, because our hardware restrictions are there for anything less than 10 nanoseconds. So it is always greater, the dt will be always greater than 10 nanosecond. So it will be dPV will be equal to difference between previous value of PV and last value divided by dt. Else you just make it 0. Now the P is equal to Kp multiplied by error, I is equal to I error, D capital. Now we are coming out to capital P, capital I, capital D. So initially we started with small kp, ki, kd, then capital Kp, capital I, ki, capital Kd. Now say PID, and output is nothing but an addition of all three plus a bias output. Now we will simply say that implement anti-reset windup, which right now we would not like to discuss because that's a different topic. It will be covered later. Now return the temperature output. The output will be returned through this function. This is how simply you have to consider OP is equal to OP0 plus P plus I plus D. Now, is it possible to implement this using machine learning? Yes, it is possible. That is the current topic of research, and we will be taking help from one of the control engineering experts from US. their learning, their site and their material etc. will be used in further videos, and we will mention about that site in the next video onwards. So in the next video we'll be building a remote PID controller. That means suppose you are keeping this PID controller in far off place in industry, and a temperature controller is having an Ethernet connection. That means you are nothing but the controller is sitting far off, so there is an Ethernet connection, and this entire thing will be in a PC which runs all these algorithms. So this is going to be a machine learning PID controller. This will be a PC connected to Ethernet, and it will be going through a temperature controller. It's exactly like earlier diagram, except you can draw a straight line, except that it is sitting in far off place, and also it's a machine learning PID controller, and heater temperature is coming back, and SP is here. SP minus the sensor temperature is nothing but the error. The process variable is the error. SP minus PV is the error. And we will see you in the next videos, and all the any programming related to this video will be given in the description. Thank you.